When a major company deploys a large language model today, they almost always rely on a built-in safety net. The prevailing assumption across the enterprise sector is that post-training alignment makes these models structurally secure against malicious use. But the empirical data shows otherwise. Recent tests yield a 98% attack success rate against models aligned using direct preference optimization, or DPO, a common method of fine-tuning behavior based on human ratings. An attacker can break these safeguards with under 30 minutes of compute time. Superficial alignment protocols provide a false sense of security against mathematically targeted exploitation. Consider how organizations handle sensitive data. The standard defense is masking, using regular expressions to automatically detect and replace explicit identifiers, like names or dates of birth, before the text reaches the model. In practice, regex masking tops out at a 42.9% success rate. High-value targets like social security numbers and medical record numbers remain highly vulnerable. When you feed a redacted prompt into an LLM, the model doesn't process blanks in isolation. It analyzes the surrounding context. Through probing, it uses latent linguistic relationships learned during training to calculate probable missing values. It reconstructs the unmasked target data with total certainty. Masking the input does not erase the model's memory. If sensitive data lives within the training weights, context will inevitably extract it. This is an image showing the outputs of two different models given the same malicious prompt. When data masking fails, the next layer of defense is alignment training, which teaches the model to refuse harmful requests rather than actively comply. This behavioral training generally falls into a four-tier hierarchy: supervised fine-tuning, direct preference optimization, reinforcement learning from human feedback, and constitutional AI. Right now, direct preference optimization is the industry favorite because it skips the need for a separate reward model, making it incredibly cheap and easy to implement. But DPO and supervised fine-tuning, which trains the model on a dataset of correct examples, share a critical flaw. They only create shallow behavioral modifications rather than deep structural understanding of why a prompt is dangerous. Relying on these cost-effective alignment methods creates behavioral boundaries that look robust to users but are incredibly shallow to attackers. This vulnerability is exposed by a mathematical process called obliteration. Obliteration entirely removes an LLM safety programming without retraining the network or destroying its core capabilities. Visualize the core weights of an LLM as a 3D environment, W. Because alignment is shallow, refusal behavior is isolated to a single direction, R. Attackers use orthogonalization to mathematically subtract this refusal vector, leaving the original network completely functional. Because this happens at the weight level, the model literally no longer contains the mathematical concept of refusal. All API-level prompts designed to enforce safety are rendered useless. Enterprise safety is not a fundamental law of the model. It is a fragile mathematical vector that can be deleted in minutes. For closed API frontier models, attackers cannot access the internal weights directly. Instead, they rely on prompt-level exploitation. And this brings us to Tempest attacks. Tempest strategies use tree-based, multi-turn prompts specifically designed to bundle requests and suppress the model's refusal mechanisms over a continuous conversation. When exposed to novel Tempest prompts, guardrail benchmark scores for these models crater from the 90th percentile down to roughly 33%. This stems from an underlying architectural limitation. Modern LLMs only have a 43.7% pass rate when given strict positive instructions, like performing complex string manipulation. If a massive model lacks the architectural capability to follow strict positive instructions, it will inevitably collapse under targeted attempts to break its negative constraints. The enterprise sector often assumes that massive frontier models, trained on the entire internet, are inherently better and safer due to their scale. This diagram illustrates the BioGPT architecture, a system where the inputs restrict pre-training entirely to targeted biomedical literature. Small-scale, domain-specific models like this act as the primary structural defense against data leakage and alignment stripping. Because the pre-training is aggressively narrow, the model physically lacks the broad and tangled web of general knowledge that enables contextual leakage in the first place. Tightly bounded models like BioLinkBird, running on just 340 million parameters, routinely beat 4 billion parameter general decoders in accuracy for specific tasks. A tightly bounded, specialized model mathematically limits the attack surface, providing superior security and privacy over a generalist giant. This text output demonstrates the second pillar of true defense: active reasoning modalities. The model explicitly details its step-by-step reasoning process before providing the final answer. Forcing the model into this active thinking mode requires it to evaluate the actual intent of a prompt. This mechanism drops Tempest attack success rates from 97% to 42%. This chart categorizes evaluation metrics for understanding versus generative tasks. Active reasoning pairs perfectly with constitutional AI, an alignment method where the AI self-corrects based on predefined principles. This creates a continuous critique and revise loop rather than relying on shallow DPO guardrails. Secure enterprise AI is not a vendor checklist or a bolt-on patch. It requires multi-method alignment, active reasoning, and intentional architectural specialization.